Chapter 2. So we're still in the realm of linear equations, but we're going to move in towards more graphing and functions. So 2.1 is we're going to move from linear equations in one variable into linear equations in two variables. So the first thing we want to look at is what does it look like when you have a linear equation in two variables? So in one variable, we had a number line. We had something like a 2, and we'd say x is less than 2. This is what a linear equation in one variable looks like as a graph. As soon as we move into two variables, we're getting two-dimensional. So we get the x-axis and we get the y-axis. So first off, is this a line graph, and what does this line represent? So you can see that this is linear because you can draw a straight line. Now there's two segments to this line, but it is a line graph. There would just be two equations representing the two different parts. And what does this line graph represent? So the line graph is representing personal spending on medical care. So then it says describe what's happening into this graph. So to describe it, we look at the axes labels. So we see that the x-axis is representing a year and the y-axis is representing the spending in dollars. And so if I look at this linear graph, I could say that there is a constant increase in spending over time. I could say that it was higher. There was a greater rate of increase from 2005 to 2009. From 2009 until 2012, it looks like it tapers off a slight bit. And what we're going to be talking about in this chapter is, how do we represent these or talk about these in more detail? What are some features we could talk about? What about their slope, their rate of change, all of that kind of stuff? So for now, all you're going to say is that there is a constant increase in spending. And then another piece of information that we could read off this graph at this time is how much was spent on medical care in 2010. So you could say in 2010, so that's your X value. And you could look across for your Y value, and you could say that $2,200 billion was spent on medical care in 2010. Okay, so that's kind of like a real world example. There's lots of real world examples of graphs, but before we can really talk in more detail about that real world example, we need to talk about details. So the first thing is that when you plot points, we plot them as ordered pairs. They're called ordered pairs because they're pairs of numbers where order matters. So this is a list of ordered pairs: -3, 2, -5, 6, and -5, 0. And the important thing is that the numbers in an ordered pair are x and then y. So this first component, okay, is the position relative to the x-axis. So the x value, or the direction that you go left and right, is always listed first. And then the second component indicates your position relative to the y-axis. In other words, the second number tells you where to go up and down. So if I was to graph the point -3, 2, I would go -3 in the x direction, and then I would go +2 in the y direction. Or some people plot it kind of like it's shown here, where you say, okay, this is -3, this is 2, and then they intersect here. Kind of up to you. You can graph an ordered pair using two perpendicular lines that intersect, or you can do it the way that I was saying, go left 3 and up 2, and completely up to you. The next feature that's important to know about is the naming of the quadrants. So when we look at what's called a Cartesian plane, or this rectangular coordinate system, you always start by counting as the quadrant 1 being in the top right, because it's where the x direction and the y direction are both positive. In real life, this is where a lot of data happens because, time, we don't go back in time, or, a lot of data we don't use the negatives for. And then when you're going, you go to quadrant 2 in a counterclockwise direction. So this is quadrant 2, and then down here is quadrant 3, and then lastly, bottom right is quadrant 4. The points on the x-axis and y-axis would not be considered to be in any quadrant. So, first question, identify the coordinates and the quadrant of the following points. So if I wanted to identify the ordered pair for the point A, so the point A is here, And I would say, okay, I mean, you can do the intersection method and say, where does it hit the two axes? So it hits the x-axis at -3, it hits the y-axis at 2, and then this is quadrant 2. All right, pause the video and try point B and point C. Point B, if you look, I go right 2 in the x direction, and then it's down 5 in the y direction. So the coordinate is 2, -5, and this is in quadrant 4. And then lastly, point C, you don't go left or right, so the x value is 0 and the y value is 5. And it's not in a quadrant. We would consider this a y-intercept because it's on the y-axis. All right, moving on. Now we want to label the coordinates and identify their quadrant again. So this time they're giving us the ordered pair and we're putting it on the Cartesian plane. So -5, 0 means I'm going to go left 5 and then don't go up or down. So this is my point D. It is not in a quadrant. It is an x-intercept. E, I'm going to go left, so a negative direction for x, and then down, so a negative direction for y. And I'm going to put my point here. And this is in quadrant 3. And then lastly, point F, and hopefully you've paused the video and come back. If not, do that now. But point F asks you to go 4 in a positive direction and then 1 in a positive direction up. And this would be point F, and it's in quadrant 1. All right. Objective 3, we're going to move from just some basic information about points back to this idea of there being an equation. So this is a line. There is an equation for this line. In fact, it's x minus y equals -3. And what we want to look at is what does that mean? So if I were to pick 3 random ordered pairs on the line, I could pick a point here, I could pick a point here, and I could pick a point here. So this point is 1, 4. This point is 0, 3, and this point is -2, 1. These ordered pairs, -2, 1, 0, 3, and 1, 4, are all points on the line. So what does that mean? Well, now, instead of just having one value that satisfies an equation, we need a point that satisfies an equation. So all of these points are on the line. So all of these points should satisfy the equation, which means if you have a line that's x minus y equals -3, the points that satisfy this equation will be on the line. So if I wanted to check if -2, 1 is a point on this line, I could plug in x is -2, so this is for the point -2, 1, and y is 1. So in for the x, and anytime I substitute in, I always substitute in brackets. So for example, if I know if I'm going to replace y, I can put y as a bracket, and then whatever y I'm replacing with goes into the bracket. And then I'm checking if that equals -3. In other words, does left side equal to right side? -2 minus 1 is -3, so yes, the point -2, 1 satisfies the equation. So any point on here will satisfy. Anything out here, like if I was to check a point -3, 5, which we know is not a point on the line, it will not satisfy the equation. When I plug it in, I get -8. Does not equal -3, so -3, 5 is not a point on the line. So saying that, we can find points that are going to satisfy an equation without having the graph. So for example, if I wanted to say, okay, well, what y value would occur if an x point of 0 was the x value of my ordered pair? So if I said, okay, I have the line 2x minus y equals 0 or equals 2, and if I wanted to say what would happen when x is 0, I can solve for the y value that would make this true. Now 2 times 0 is 0, so -y equals 2, so I'm going to divide by -1. Oops, that's supposed to be a negative sign. And I get y equals -2. So the point that would satisfy the equation is that when x is 0, y is -2. And I can do it the same way as well. The next one, so this is when x is 0. The next one I'm going to solve for is when y is 0. I take that same equation, 2x minus y, equals 2, but this time I'm going to substitute in for y. And I'm going to substitute in 0. Again, 2x minus 0 is just 2x. And then I would divide by 2, and I get x equals 1. So the point on the line that will satisfy the equation would be 1, 0. And then lastly, when x is negative 2, I plug into this equation. Again, whatever I'm going to sub in for, I just replace it with a bracket. You can even do it right before. Put a negative 2 in there. 2 times negative 2 is negative 4. And then I'm going to add 4, negative y equals 6, divide by negative 1, and I get y equals negative 6. So when x is negative 2, y is negative 6. All right, next objective, graphing lines. So if I wanted to graph the line 2x minus y equals 2, I could use this what we call a table of values. So these points that I've solved for. So the points are, just because I'm going to have to scroll down, 0, negative 2, 1, 0, and negative 2, negative 6. These are the 3 points that I've solved for that are on the line. So I'm going to say, okay, I know that 3 points are 0, negative 2, 1, 0, and negative 2, negative 6. I'm going to know that I did this right because they should all be able to connect and make a line. If they don't, then I've made a mistake. And the question is, can I connect these? And the answer is yes. So these are just 3 points, 3 examples of points that are on the line, but there's an infinite number of points that are on the line. So I'm going to connect my dots as best I can. There we go. And the next question is, can you extend your line beyond the ordered pair? So like beyond here and beyond here? Yes, because I did it. In fact, you can extend it beyond your grid. When you're graphing a line or something that does not have a restriction to it, they will always go off. So you extend past the end of your Cartesian plane, and then you put arrows on the end to show that it is extending. Did you need all 3 points to graph? Well, not necessarily. You need at least 2, but I always say 3 or more is best. It's just 2 is okay, but sometimes it's hard to make a straight line. 3 kind of makes it a bit straighter, and then if I had done even more, then it would make it even better. So how many points do you need to start graph a line? Technically, you only need 2, but I'm going to say at least 2. All right. Let's take a break here, go and do some homework, and come back and do the next video.